Seismic evaluation of fiber-reinforced elastomeric isolator with different irregularity conditions in building. Abstract. The growth in seismic isolation technology has led to the development of numerous innovative and unique base isolation devices. Fiber-reinforced elastomeric isolators, FREIs, are low-cost alternative to conventional steel-reinforced elastomeric isolators, SREIs. FREIs are light in weight, easy to manufacture and cheaper than SRFIs. Fiber-reinforced elastomeric isolators, FREIs, comprise alternating bonded layers of elastomer and .Bur reinforcement sheets. A partially bonded fiber-reinforced elastomeric isolator, PB-FREI, is achieved by partially bonding the top and bottom surfaces of the bearing to its contact supports. This study investigates the performance of partially bonded fiber-reinforced elastomeric isolator under stiffness irregularity and mass irregularity conditions. Keywords: elastomeric isolator, mass irregularity, stiffness irregularity. Introduction. Fiber-reinforced elastomeric isolators, FREI, are a relatively recent development in the field of base isolation. The benefit of FREI is that they have the potential to be a lighter and less expensive alternative to current rubber isolation devices, such as low-damping rubber and lead plug rubber isolators. Traditional isolators are comprised of layers of rubber and rigid steel shims that provide the bearing with vertical stiffness. By replacing the heavy, steel shims with lighter layers of fiber that have an elastic modulus similar to that of steel, studies indicate that FREI are able to satisfy vertical stiffness requirements for an isolator. In addition, the use of fiber as reinforcement introduces an additional flexural type response component into the isolator that affects its horizontal stiffness. Fiber-reinforced elastomeric isolators, FREIs, comprise alternating bonded layers of elastomer and fiber reinforcement. The prospect of a lighter and cheaper alternative to current rubber isolation devices prompted research into using FREI to isolate low-rise masonry buildings and bridges. There are three types of application for fiber-reinforced elastomeric isolators: bonded FREI, unbonded FREI, and partially bonded FREI. In a bonded FREI, two thick steel mounting plates are bonded to the outer rubber layers at the top and bottom of the isolator. During installation, the top and bottom mounting plates are bolted to the superstructure and substructure, respectively. In a UB-FREI, the isolator is placed between the substructure and superstructure without any bonding or fastening provided at its contact surfaces. As such, the shear loads at the bearing contact surfaces are transferred through friction only. In a PB application, only portions of the contact surfaces of the bearing are bonded to the upper and lower mounting plates. A cant amount of the tensile and shear forces can be transferred via the partial bond. The bearings were made from alternating layers of cold vulcanized neoprene and carbon .Bur fabric. Two objectives: to investigate the performance of FREI under stiffness irregularity, to study the behavior of FREI under mass irregularity conditions. 3. Summary of literature review. Fiber-reinforced elastomeric bearings, FREB, comprise alternating bonded layers of elastomer and .Bur reinforcement layers. A PB-FREB is achieved by partially bonding the top and bottom surfaces of the bearing to its contact supports. Studies were mainly carried out on the results of a comparative experimental study between UB-FREB and PB-FREB. 1. A comparison of the seismic response of steel frames by using IJERT types of bracing systems were mainly carried out. 2. FREI matches the behavior of an SREI, consequently, the FREI could replace the conventional SREI for seismic isolation with low-cost manufacturing and lightweight installation. 3. By increasing the maximum imposed shear strain, the area of the isolator surfaces in contact with the concrete blocks decreases and, as a consequence, the isolator average horizontal stiffness also decreases. 4. For numerical analysis. The analytical study includes the development of finite element models to evaluate the performance of a partially bonded fiber-reinforced elastomeric isolator with different irregularity conditions in a building. ANSYS Workbench 16.1 software was used to perform the seismic evaluation of partially bonded fiber-reinforced elastomeric isolator with different irregularity conditions in building. A. Material properties. The material properties of the partially bonded fiber reinforced elastomeric isolator are tabulated in Table 1. B. Base model. ANSYS 16.1 Workbench software was used to model the partially bonded fiber reinforced elastomeric isolator. Length and width of the partially bonded fiber reinforced elastomeric isolator was 100 mm. A FREI pad of 100 x 100 mm comprised of 4 inner layers of elastomer of 4.5 mm thickness, and 2 outer layers of 2.5 mm thickness is modeled. The total height of the isolators is approximately 25.5 mm. The total thickness of the rubber layers is TR equals 23 mm. The shape factor of the isolators is S1 equals 5.56. The aspect ratio is approximately S2 equals 3.92. The elastomeric laminated rubber isolators, a cover rubber layer is bonded along the perimeter of each isolator to provide protection against oxygen and ozone attacks. 2 square-end steel plates of 100 mm width are partially bonded across an area of 50 x 50 mm at the center of the outer elastomer layers. Fig 1 presents the isometric view of partially bonded fiber reinforced elastomeric isolator. Fig 1. Partially bonded fiber reinforced elastomeric isolator. The specimen is placed in the 4-story building and 3-story building. The plan of the building is selected as per Dia Edin Nasani ETAL2. The front view of the 4-story and 3-story are shown in the Fig 2. The total height of the 4-story building is 16.47 m and the height of the 3-story building is 12.81 m. Fig 3. Stiffness irregularities of buildings A, 4-story stiffness irregularity 1b, 4-story stiffness irregularity 2c, 3-story stiffness irregularity 1d, 3-story stiffness irregularity 2. The PB-FREI is placed in the 4-story building and load is distributed in all floors, 4s. Top story of the 4-story building is unloaded and the other 3 floors are loaded, 4s mirror at 4. Then the 3rd floor is unloaded and remaining floors are loaded, 4s mirror at 3. Similarly the 2nd, 4s mirror at 2, and 1st floor, 4s mirror at 1, is unloaded and remaining floors are loaded. Similarly the 3-story building mass irregularity is also considered. 2 stiffness irregularity conditions in 4-story and 3-story building are shown in Fig 3. V. Results and discussions. The results of numerical analysis such as isolation displacement, top story displacement and shear stress on corner, exterior and interior under mass irregularity is shown in Table 2. The story displacement graph of 4-story and 3-story mass irregularity are shown in Fig. 4. The story displacement graph of 4-story and 3-story stiffness irregularities are shown in Fig. 5. The results of PB-FREI with stiffness irregularity is shown in Table 3. From the story displacement analysis as shown in Fig. 4, it is observed that the displacement increases with increase in story length. The dia placement is maximum at the top of the building. The results of partially bonded fiber reinforced elastomeric isolator with mass irregularity is shown in Table 2. The shear stress is maximum at the isolators on corner and shear stress on exterior is minimum. 6 Conclusions. In the present study, partially bonded fiber reinforced elastomeric isolator were introduced in the building and the behavior of PB-FREI under mass irregularity conditions were studied. 4-story building and 3-story building were considered. Further, the performance of PB-FREI under stiffness irregularity conditions were also studied. From the result obtained from this paper it can be concluded as follows. The displacement is maximum at the top story of the building. The top story displacement is more than the isolation displacement. Shear stress is maximum at the isolators on corner and shear stress is minimum at the isolators on exterior.